He's a keen promoter of physics and in public engagement in science, and he's held several senior positions in both the Institute of Physics and the British Association of Science. So, Nigel, if you'd like to take it away.
Thank you, Joe. Well, welcome everybody, say once again. On my opening slide, you see a set of pictures here, and every single one of these pictures is something that I have worked on. And you see, and I'll cover most of them in the talk, but I want you to give an idea of the range, because one of the great advantages of being an academic and as you get older is you can sort of use your expertise in different applications. And that's the message I really want to get across to you in the next 45 minutes. Now, I think it's quite interesting just to sometimes to see how I got to where I am today, if you like. The first thing is I didn't have a choice about being a physicist, really, because my father was a physicist. He was actually a very famous physicist because he was the UK's first professor of cloud physics. And if you type the Mason equation into Google, you will find there's even an equation which is named after him, which is about how raindrops grow in clouds. And he was Director General of the Meteorological Office, the British Weather Forecasting Service, as well as being various other posts, including Chancellor of UMIST and various other things. So I was brought up in a household with an older brother who was clearly not wanting to do science. He hated anything to do with science. So my brother went into economics, which isn't really a science, and he works in the Ministry of Transport and is quite senior in that. So I was the younger one, so I was told, you know, we really should do science. So I did. And I went to UCL and I did my PhD there in an experiment where I looked at electron scattering in a laser field. And we actually did an experiment which demonstrated that you can combine the energy of a photon from the laser field with the kinetic energy of the electron to excite helium into its excited state. And this was first forecast in 1927, but we first demonstrated it in 1986. Because of that kind of pioneering experiment, I was very fortunate to get a position called a Royal Society University Research Fellowship, which I held for 8 years. And this was a great thing to have because it enabled me to do whatever I wanted to. And so I was interested in looking at molecules. So I set up the molecular physics group at UCL. And this was just the time of the ozone hole being discovered. And thought, well, that's interesting. I did say it to my father that I would never do anything in atmospheric physics. And of course, within 10 years, I was studying clouds in the Antarctic and to do with the ozone hole. But interestingly, if anybody know about the situation of the ozone hole, it turns out that the chemistry of the ozone hole is nothing to do with gaseous phase. It's to do with particles, icy particles, and particular types of ice particles in the polar stratospheric clouds. So I started to do experiments on ice particles, which is what my father had done when he was younger, as I say. So I decided I'd never do anything with him and ended up doing it. So when I finished my Royal Society appointment, I was appointed a lecturer and then a reader at UCL. And we had a famous professor came from Manchester, David Williams, who pioneered the field of astrochemistry and said, molecules can form in space, but we don't really know how. We've never really done any experiments about them, but you're working on sort of icy particles. But astrochemistry, well, there's dust in space. Could you do experiments there? And I said, yeah, we could do experiments there. The only difference is instead of working at 220 Kelvin, we need to work at 10 Kelvin. So instead of using liquid nitrogen, we used to need liquid helium, which costs about 10 times as much. So I got into that and we started those experiments. And then in 2002, I was invited to be a professor, head of school of Department of Physics at the Open University. And I joined them at a very exciting time because that was the time of the Beagle mission, the UK's mission to Mars with Colin Pillinger. And also at the same time, actually, they just moved a large group of people from Kent to the Open University. So I joined at that exciting time when we were expanding out that. And of course, as you can see, yes, last night we're landing things on Mars. Unfortunately, Beagle did land, but it never opened up properly. But that got me into planetary science. And so from the last 20 odd years, I've been involved, particularly involving in planetary science and looking at things in Titan and so on, and looking at the emerging field of astrobiology and the search for life elsewhere. And I'll be talking to you about that again in a few minutes. But my feeling and my interest in working on the small scale, the atomic and molecular physics scale, means that I still work in the nanotechnology area. And I'm going to give you some examples of how we can manipulate things on the atomic and molecular scale, particularly on building nanostructures and also in radiotherapy. And so I was at the Open University in 2018 when I then joined Kent as the head of school and also the headquarters of the Great Euro Planet Project, which is also headquartered there. So I'm going to give you a bit of a journey about the things that I do. So I'm a peculiar person because I'm a physicist, but some people think I'm a chemist and some people think I'm an astronomer. And some people even think that I understand radiation biology. Actually, I don't understand any of it, but I'm quite prepared to have a go to try and understand it. But my first area, my first passion is to study molecules. And molecules are small. And so therefore, I tend to work on the nanoscale. But as I say, the molecules and their reactions, for example, determine how planets form. And if you don't understand how molecules form, you can't understand how life emerges. So I study space, which is also very big. So I work at the small scale, but the applications are often on a large scale. And as I say, what I'm going to do is give you some examples. So I like doing physics with applications. And my father gave me one piece of advice when I was starting off in the field. He said, don't get stuck. Every 7 years, think what you're doing and think about doing something new because it will keep you engaged. And I've taken that advice. And right at the end of this talk, I'll tell you what I've decided to do in the next 7 years. Carrying on using my expertise, but doing things that are different. So let's start with the very small. Now, the very small, what you're most used to is watching this on your computers and having your mobile phones. And that's making small things and small computer chips. So plasma technology is all about making things small and making them smaller and smaller. Now, to make a computer chip, what you basically do is you make a plasma and you etch silicon to make structures. And that's been developing for the last 30, 40 years. But we have two problems in the technologies today. The first one is we can't really make things any smaller than they currently are. We're down to about 10, 12 microns. You can't make structures smaller than that with plasmas. It's quite difficult. And the second thing is all the gases you need and all the things you need to etch, which basically means eating away at the silicon, none of them are very nice gases. And the problem is they're not only not very nice gases from like chlorine containing compounds, but they're not very good for the environment. And a lot of these leak out into the atmosphere and they produce things like the ozone hole. But more importantly, nowadays, they also produce global warming. So in 2002, there was an international project decided that we really needed to change the gases. But the problem is that nobody really knew how these plasmas worked. And we still don't really have a perfect idea of how they work. And if you want to set up a plasma etching company, like the big companies do, you have to etch silicon wafers about a few inches in diameter. And you have to have a success rate on your chips of something like 97 or 98% to be commercially successful. So you've got this wonderful tool, but you don't know how it works. And then somebody comes along and says, can you please just change all the gases you're using to do the etching? Well, that caused a bit of a panic in the community because they didn't understand it. And so we started a collaboration, particularly between the European Union and Japan, partly because the Japanese are much more freedom in giving us able to publish things, whereas the American companies insisted that we could do the research, but we weren't allowed to publish anything. And if you've got lots of PhD students, the idea of the fact that a PhD student can't publish anything is not very good for their careers. So we've been working with the Japanese since 2002. We have a nice meeting every year. 1 year it's in Europe and 1 year it's theirs. Last year it should have been on the lovely island of Okinawa. We couldn't go. This year it was supposed to be up in the Slovakian mountains. We haven't been able to go. So they've all been online. But these are some of the things that we can do. We now use a technique where we had the plasma and we etch the surfaces, and we can make these structures, as you see down the bottom here, about 50 nanometers in size. And that looks good. That's great for producing your chips and so on. And the idea is that if you can make smaller and smaller features, you can get more and more power, so your chips can get more and more powerful. And there's something called Moore's law, which basically says that we've been so successful that every 18 months or so, we can double the power of the chip. And we've been able to do that by making the chip smaller and smaller and smaller. But as you can see from this diagram here on the transistor sizes, we are slowing down. We've got to the stage now at the bottom of that graph where realistically, we can't make these things much smaller by the plasma etching technique. So we're kind of stuck down here, just as you can see, a little bit below 10 microns in size. But even those 10 micron size ones, they're not as efficient. They have errors in them, and you don't want an error in your phone, and you don't want an error in your chip in your computer. So we had to start to think about doing it the other way round. Rather than start with a big lump of silicon and etching it to make it very small, why don't we try and build the structures from the bottom up? Why don't we take the molecules and see if we can build the structures from the bottom up? And that's where somebody like me, being a molecular physicist, is interested. So we now have some new techniques. And one of these techniques is called focused electron beam induced deposition. And basically what we do is we take some molecules and we fire at them in a gaseous jet. You can see them coming in here in the figure on the right. We fire an electron beam in them at very high energy, and they basically make break up these molecules, which are basically something made with an iron or metal atom in the middle, surrounded by some carbonates or something around, and the electrons strip off all the things left, and what should go down on the surface at the end is just the bare metal atom. And so we can start to build the structure atom by atom on the surface. At least that's the principle. And here is a map this is, I think, still the record. This is a map that's been built like this. This is actually made of iron atoms. And once you've got your electron beam going onto the surface, you can move it around with just X, Y, Z, well, X and Y, it's only on 2D surface position. And you can draw out structures and you can build them up. So this we think is the smallest map of the world, okay, ever made. The width on the screen here across the whole thing is 230 nanometers. And it's been built using this FEBIB technology. And it's not bad. You can see there, you can just about see the attempts to get the UK up there, but that was a bit difficult. Australia looks a bit funny, but I don't think it's too bad considering, you know, we're trying to do this there. And that's about the best that we can do. So it gives you an idea of the spatial resolution that we can build with these things in this new technique, in this new technology. But I'm afraid you have to do some chemistry to do this. It's not just physics, you have to do some chemistry. And these are the sort of molecules you use. You can see here I've got a platinum atom surrounded by all these other structures. And basically what my electrons do is strip off all these other structures so that I only get platinum atoms going down. And I can do it with platinum, I can do it with gold, I can do it with iron. Iron's great because then I can make magnetic structures. I can make magnetic nanostructures. And we do this again in a collaboration between academic and industry. And we're fortunate enough to have funding from the European Union and also from Japan. We had a project called ELENA, which is just finishing next month. But fortunately, we have another project to take that over called RADON. And you can see here on the left-hand side, you see the picture of the world, our smallest ever map of the world. But on the left-hand side, you can see we can make these structures. And what you've got here is a 5 nanometer pitch. You can see we can make nice straight line structures, which are ideal for electronics. And this, we think, is one of the new technologies that we'll be able to build. Okay, so what about other things that we can do on the nano scale? Well, the great thing about one of the other great challenges is health. And until the pandemic, the biggest area perhaps that most people were interested in health, and the thing that most people would die of, and 50% of all of you will get cancer. That's almost inevitable because we've already eradicated everything else. So if we get on top of the COVID, The most likely thing that you're going to suffer, 50% of us are going to suffer from in our lives, is cancer. And we've been trying to develop new technologies for cancer therapy. And there are two techniques which have been developed in these next generations, and they both involved nanoscale effects. Now, all you need to know for a quick guide of biology, and all the physicist needs to know, is that if I've got some DNA, which is what basically the cancer problem is it's self-replicating DNA, but replicating incorrectly to produce these cancer cells. If you want to destroy the cancer cell, you need to destroy the DNA, and you can break it up with two ways. You can hit the DNA itself in the cell with radiation and just basically blast it. Or because the cell is in a cell, it's got a lot of water, and you break up the water and you produce OH radicals, which also do the damage. And about 1/3 of the damage is produced by direct radiation, and about 2/3 by the water. Okay. Now, what we've discovered is the fact that it isn't the primary radiation that makes all the difference. It doesn't matter whether you fire in an X-ray or a gamma ray or an ion beam or UV light. Basically, what happens is that you liberate a lot of secondary electrons, and most of the chemistry and most of the physics and many of the processes which we now see, from the plasmas to space, involve these low energy electrons. Electrons are the universal thing that induced a lot of physics and chemistry. So we started to look at what happened if you took electrons and you shone them on DNA. And in 2000, there was an absolutely classic experiment that showed a very strange pattern. And this is something that you can't go into great detail, but what I've got here is a damage spectrum of the DNA as a function of electron energy. And the thing you need to note is, first of all, the electrons are low energy. Indeed, they can almost be zero energy, but they can still break up the DNA. And the second thing is there are two types of DNA damage. There is a single strand break, where you just break one bit side, if you like, of the DNA. That can be repaired by the cell relatively, well, not easily, but it can be repaired. And then there is a double strand break, where you basically break simultaneously or close to in time the two strands, the two sides of the DNA, and that can't repair very well. So the single strand break repairs, but might repair incorrectly, and that can be one of the real problems with the cancer. You've got the wrong type of cell. The double strand break is what we want to do, because we want to put that into the cancer cell and kill those cancer cells. But what I want you to just notice here is, A, the energy for breaking up the DNA is very low energy. And secondly, it's not smooth. It's got these kind of bumps in it. And this is a fundamental phenomena of how electrons interact with molecules at low energy. And it's something called a resonance, where the electron attaches itself to the molecules for a while. And then when the electron comes off, it breaks up the molecule. And this process, which is something called dissociative electron attachment, is being seen just about everywhere. It occurs in space, it occurs in plasmas. It's one of the main reasons why we break up those molecules in the Febib process I just showed you. It occurs everywhere. And that's a physics process that we have to understand. We now have a good understanding of trying to understand how DNA is damaged, and we have lots of models, and we do lots of experiments. They're done by physicists, they're done by medical physicists, often people with a boundary between physics and understanding the biology. It's modeling and it's experiment. And from that, we've been able to design some molecules that you can put into the cancer cell, which, when it is irradiated, destroy the cancer cell, but maybe aren't taken up by the non-cancerous cell. So you're targeting the cancer cell, but not the other one, the good ones. And the molecules which we've designed are something called bromouracil. It's called a radiosensitizer because it's much more sensitive to radiation. And it goes in and it basically replaces one of the components in the DNA chain, one of the nucleotides in the DNA chain. So we can do that. Or what about using nanoparticles as a way of getting the particles into the body and into the cells, or into just as a drug? So we're doing that. We're using this newer technique of nanotechnology to design nanoparticles as means of drug delivery. And we're using them as radiosensitizers. Some nanoparticles are preferentially taken up by the cancer cells. So you build up a concentration of these nanoparticles in the cell. You have to understand the physics of them and a bit of the structure of them and how they attach to the membrane and how they move through the cell. And they have to be usually things. Gold is very good because gold is not poisonous. It's not a toxic metal in your body. You can have gold in your body. That's fine. And then you're going to think about what more. And then you can target a drug onto the nanoparticle. You can put the drug onto the nanoparticle and then inject it into the cell or get it just taken up into the cell. And again, we're fortunate is the way that research is done these days. These are done in collaboration. So we had a collaboration called Argent, which brought together physicists, people from the chemistry, from the drug industry, people who did modeling, people who did experiments. And this is the way that work's done these days. We work together in big collaborations and we build the models. Then we develop the model for trying to understand how that works. And we have to design the model that tells you how we're going to treat the patient. We have to decide how much radiation we can put in, how we're going to put it in, etc. And we also have to look at the toxicology and so on as well. So, you know, you have to get all the people together. So here's the classic picture, just to show you that what we've managed to achieve. If you just put gold into the body and you irradiate the body with, say, an X-ray, you can see the different. It doesn't do anything. The gold itself doesn't really do anything. It's the same as having no treatment at all. If you irradiate the cell with no gold, just irradiate the cancer, you can see there the tumor volume. This is actually, sorry, it should actually say decrease in tumor volume. It shouldn't say tumor volume, so I've missed out the decrease. This shows you that the decrease in the tumor volume basically it shrinks over a period of days. If you irradiate it with the gold in the particle as well, you can see that essentially I can kill the tumor. So that's what we do on the very small scale. We're basically taking the idea of trying to understand molecules, trying to understand the physics of how they work, etc., on the small scale, build these nanoparticle devices, make these nanoparticle structures, use nanoparticles as a cancer therapy center. But what about going to the very big scale? What about trying to understand physics in space? And these are two projects which I was involved with. The one on the left is the Cassini-Huygens. It's the classic experiment. It's classic mission. It's the first mission that Europe actually built a space instrument. The Huygens probe was built by Europeans, but went on the NASA mission, the Cassini mission, and went down through the atmosphere of Titan and took the pictures of what Titan was like. In fact, the very first thing to land on the surface of Titan was something called a penetrometer, which is basically to see whether the surface was hard or soft. And that was actually designed and developed at the University of Kent by John Zanecki, who then joined me at the same time I moved to the Open University. And we now know a lot about Titan. And we kind of think that Titan might be a bit of like a primeval Earth. It's got all the kind of ingredients of how the molecules that you need for life to begin might have started to come together, but it isn't quite there yet. And the other mission I was involved in, I'll talk a bit more about, is Rosetta, which is again a European mission, which actually went to a comet and landed on a comet. My colleagues at the OU built the mass spectrometer that was on the probe that landed on the comet. And we wanted to look and see what kind of molecules there were on that comet. And they're all put together here in this slide. It's called the Cometary Zoo, trying to group together the type of molecules that we believe, and there's still some controversy between the various members of the team of how many of these we've actually seen or not. But I think it still shows you an idea that that comet was showing a lot of molecules. Now, the big question is, you know, why is there any chemistry out there on a comet? Or even more, why is there chemistry in space? These are all the molecules that we found in the interstellar medium, those regions between the stars, which is where the stars form and where the planets form. And this is a complete list. Maybe it's a little bit out of date, but not much. These are some of the molecules that we've had interested in. Formic acid, which is basically get from squashing ants. So we've got formic acid in space. We've got acetic acid, or we've got vinegar in space. We've got a glycolaldehyde, which means we've got sugar in space. And maybe we're starting to see, and we're still hunting for it, we're starting to see the first sort of amino acids like glycine. We've also got things like benzene. We've also got molecules which we don't find on Earth, like this one, which is a very long chain molecule of carbons with a hydrogen on one end and nitrogen on the other. We don't see that naturally on Earth, but it's certainly there in space. And the question is, how do you make all these molecules? Because in the 1970s, it was thought there wouldn't be any molecules in space. There couldn't be. Space is cold, 10 Kelvin or less, and it's empty. So you can't do chemistry when it's cold because no chemistry reactions. You have to heat things up to make chemistry work, don't you? And it's empty, so the molecules never meet each other. Well, that's not, but they're there. But David Williams, as I mentioned, who came to UCL, he pioneered the field. He worked out, well, yeah, that's true. But actually, in most of these regions where we're seeing chemistry, this is where the stars and the planets are forming, and they form from dust. And they're full of dust, which is basically made of either carbon or silicate material, very small, probably on average about 10 microns in size. But it's a surface, and it's a surface that's very cold. So the few molecules you can make in space, which are made by iron molecule interactions, which are very interesting interactions because they don't need any energy. They are exothermic reactions. They are formed, and these molecules then descend onto these dust grains, and they stick to them. And over a period of time, and you've got lots of time in space, you gradually build up a kind of icy fragment, an icy surface. And in these icy surfaces, you can irradiate them with cosmic rays, ultraviolet light from the star, maybe being formed when it's formed. You can heat them up by shocks and everything else. And this was felt that how you'd get your chemistry. But what we do know from what you've heard earlier is actually all of these things, the cosmic rays, the UV light, etc., produce electrons. And in fact, one cosmic ray can produce about 10,000 electrons. So we started to say, okay, what happens if we take these ices under chemistry conditions and we irradiate them in the laboratory? Can we make the molecules that we see? So here's a very simple experiment I'm going to do for you now. This is just basically a spectrum of water and carbon dioxide ice. And I've got some bands here, which are either due to showing me that I've got water there or I've got CO2 there. And I can irradiate it for about an hour with electrons, or actually ions or anything else. It doesn't really matter. And I will start to see some new features occur. And it's not difficult to work out what's happening. The first thing is I get CO2. And if I break up CO2, I get CO. So I got a CO peak. Good, that makes sense. I've then got an oxygen atom left over. So that kind of combines with the CO2 to make CO3. Doesn't survive long in the gas phase because it's a radical. But in the ice phase, it lives there. And then it reacts with the water to make carbonic acid. And so by irradiating a mixture of water ice and carbon dioxide ice, I can make carbonic acid. And why is this topical now? Well, the reason is, let me just heat it up first. Let me just do it. If I then heat up the ice, if I heat up the ice and I evaporate off the water and the CO2, the temperature's on the left, and I evaporate those off, I'm left with my carbonic acid. And the reason why it's topical is this is what happens on Mars. The Martian ice caps are made of water and CO2. In the seasons, they are irradiated by light, ultraviolet light, and so on, and some cosmic rays. And they are broken up, and the ice caps recede, and what you're left with is carbonic acid. And the carbonic acid, then being an acid, can actually erode the rocks and minerals around. And we need to understand that if we need to understand what we're going to see when we go to Mars and try and look in some of these regions. We're going to form these carbonates. And these carbonates are one of the essential things that they want to look for in the rover that's just landed, because carbonates are also a sign of biological activity. So you need to be able to distinguish between natural activity and biological activity. And that's why we need to understand these effects. Turning now to Rosetta, as I said, the other place we went to is the comet. Now, last night you saw an absolute perfect textbook landing of the rover. Unfortunately, our landing on Rosetta wasn't quite as textbook. The little probe, which was released to land on the surface, went down to the surface, and it was supposed to sort of clamp onto the surface. It had something, it was supposed to land on the surface and fire some clamping rings to make it stay. It fired, but the surface was too hard. There was something on the surface that was so hard that we couldn't clamp onto it. So it bounced, and it bounced at least 2 or 3 times before finally coming to rest in the side of a small cliff. Nonetheless, we were able to make measurements of it, or the team were able to make measurements of it and find all those molecules. Our part of the program was working with, again, a former postdoc of mine, was we found some signatures of these as the comet moved towards the sun, it started to produce plumes, jets. I mean, if you've seen the video, if you've seen the film Armageddon and so on, you know, where they're trying to sort of plant bombs on the comet to make it blow it up before it hits the Earth. We were essentially looking at these plumes of stuff coming out. And we tried to work out the signals, and we took nice spectra of them. My colleague Dennis Budowitz took nice spectra of them, and we tried to fit them. And absolutely nothing fitted. And all the people at JPL were getting really annoyed because we just couldn't work out. It just didn't work. And the reason it didn't work is we were only using photon models. We were only assuming that all the physics and all the chemistry was being induced by the sunlight. As the comet got closer and closer to the sun, we were expecting it would just all be driven by solar light. But that wasn't the case, because actually what the sunlight was doing was ionizing the molecules, producing these electrons. And as you may know by now, that's what happens. The electron chemistry came in. And so we actually were able to get the emission came not from the photons, it came from the electrons ionizing and breaking up some of the molecules. So we now understand from the spectrometer that we can actually understand what's happening in a comet by understanding what's happening in the lab. And we now have the kind of first process of an electron-driven process in space. And that goes back to saying, well, okay, electrons can do stuff. We've seen it on the comet. Therefore, maybe all the experiments that we're doing to show how to make these molecules in the interstellar medium by electrons can work, because we've seen that electrons can actually do things. And I say, here is the list of the molecules. And I say, this is still a bit subject to debate. I don't agree with every molecule that's on this list, but I don't think we've got conclusive evidence for all of them, but these are the ones that we've seen. And just look at the range here. You've got some really quite interesting molecules which can be used to what they call prebiotic molecules that are necessary for forming more biological molecules if they came into the Earth, etc. And that brings you into the field of astrobiology. So we're still asking, can we create an amino acid? Can we create a sugar in space? How do we do that? Can it be synthesized in the icy mantles? And I guess you won't be surprised to see that, yes, we can. We can make glycine in the lab this way. So glycine is the simplest amino acid. We're still looking for it. The bigger the molecule, the harder it is to have a spectral signature to resolve it in space. But we believe it's there. And with the new telescopes, JWST and the ALMA telescope, we believe that we will establish that glycine and other amino acids are made there. So what am I doing now? What apart from getting excited about the Mars landing? These are some of the other things, and these are projects that are going to be around for when you're doing your PhDs and when you're graduating. These are the sort of studies that you can get into. The next big ESA mission is called the JUICE mission. It's to go to the moons of Jupiter, particularly Europa and Ganymede. There's an American mission at the moment called Juno, which has just been extended. Good bit of politics there. It wasn't clear that Trump wanted to do it, but Biden has sort of come in and said, yeah, maybe we can extend it. So we're going to get a flyby of those moons by the Americans, which will set it up nicely for when the Europeans arrive with the JUICE mission. We're looking at the composition of the ices and the aerosols of Titan. The orangey plume of Titan is due to something called tollens. These are basically dust made from nitrogen and carbon. And we have seen the same on Pluto. The New Horizons mission has seen similar red dust on the poles of Pluto. And soon we will be looking at Kuiper Belt objects. New Horizons is heading in there. And we'll be very, very interested to see whether we see any of these molecules on those. We're interested in studies of the moon, particularly about water on the moon. That was in the news last month about there being more water in the lunar soil. We're interested in that and ice studies of the moon and the craters there. And we're interested in how we get the prebiotic molecules to then come to the Earth through micrometeorites and other bi-impacts and looking at shock. And again, that's something we do at Kent. We have a light gas gun that can kind of mimic micrometeorites coming into the Earth's atmosphere. So we do this by experiments. We do it all over the world. We have some interesting things where we basically take spectra, because the only way you can ever identify anything in a space mission is by spectra. And we had a paper came out a couple of weeks ago, which was the first discovery of hydrazine on Rhea, which is a moon of Saturn, from the Cassini data. We tried to fit every spectral line we could think of, and we were just left with some signature that just would not work unless we saw that we could produce it was a hydrazine, which is an exciting result. We're looking at the isoradiation for juice using electrons and also by ions, because a lot of the moons of Jupiter live in the magnetosphere of Jupiter. So they're bombarded by these ions. And we have a very nice collaboration in a big facility in Hungary where we're spending our time there. And we're also looking at shock-induced chemistry, not just by gas guns, but also by shock waves to see how that changes the ices and the minerals. So those are things that I'm doing now. And as I said to you, my father's advice was don't every few years think about a new topic and go off and look for something else and use your expertise to study something else. And so I'm going to finish with the two that are for me for the rest of this decade. And the first thing is combustion, flames. We actually don't understand the physics and chemistry of flames very well. If you want to put out a fire, the easiest way is to remove the oxygen. But if you're in an aircraft or if you're in a military vehicle and it catches fire, removing the oxygen is probably, it will put out the fire all right, but it's not very good for the people inside the plane or the tank. What is known is that if you put in particular gases, sulfur hexafluoride, SF6, for example, is a classic. If you put that in, the fire goes out. And what happens is that these particular molecules, they suck up electrons like a sponge. And if you remove electrons from the flame goes out. So your flame is ionized. If you remove the electrons, it goes out. So maybe we need to understand a bit more about how electrons work in flames. And the reason for doing that is that, again, many of the molecules, this is a National Bureau's report, this was actually secret. The Americans knew about this in the 1960s as part of a space program when they had some fires. And they were trying to find out with flame retardants, which they could use. And it was all classified. You weren't allowed to know it during the space age because they put these fire extinguishers on the Apollo missions and everything else. They didn't want to obviously take away the oxygen. They had to find something which was only could be used in small quantities that was effective. And these were the molecules that they used: SF6, CF3Br, but they're not good because they're global warming gases. So we're not allowed to use those anymore, although there is actually a special dispensation. You are allowed to use these on airplanes and you are allowed to use these in the military. So we've been looking for new ones that would work, and CH3I works and FeCO5 works. And that's exotic, but that's the same molecule I'm using in my nanotechnology for building those bottom-up structures. So the molecule does two roles. You can use it to build nanostructures, or you can use it as a new fire retardant. So we're looking at that. That's one of our new areas, and we should have had a nice meeting about that last year. In November, we were trying to get all the people together from combustion communities, from the people who are building aircraft engines, car engines, the people who were designing fire retardant systems. We were all supposed to meet up in November in Leipzig, but unfortunately we couldn't. So we had to postpone that conference, and hopefully this year, well, when we get out of the pandemic, we'll be getting back into that. The other technology that we're interested in is thruster technology. Iodine is using not fuels like hydrazine, which is commonly used in space, but actually to find things where you develop a propellant where you put a small thrust, and again, good physicists will know, but all you need to do is put a small accelerating force, but apply it for a long time, and you'll basically be able to build your spacecraft to do it. Now, the gases that have been used up until now that when this works in is xenon, but we are replacing it. We're finding new things to do, and iodine is particularly good because iodine is a gas, is a solid at room temperature, and it's sublime. So there's no sticky liquids with iodine. You only just go from a solid to a gas. So it's really nice. And why do we want to do that? Is because this is going to be the next generation of transport. And it's brilliant for small things like CubeSats and nanosats that need not a lot of energy, and they don't have room for big engines and solid fuel. But if we can get thruster technology to work, then we can use these as the main thrusting potential for many of these small CubeSats, or even just small amounts to make them maneuver, to put them into combinations, to make them to form arrays. And again, it goes back to understanding basically plasma physics, electron interactions with things like iodine. So that's the two things I want to work on in the next decade. But I hope I've shown you that you start off in a field of physics. You choose a PhD topic, which was completely abstract. I was just fascinated by this idea of electrons and scattering. I was interested in Aurora. I've seen those. And I thought, well, you know, I'm going to go and do something, and I'm going to look at electrons scattering off an atom in a laser field. Nothing my father does. I'm not going to go anywhere near atmospheric physics or anything else. But then the applications came along, the ozone hole came along, and you start to apply your knowledge of collision physics and spectroscopy to new areas. So first of all, atmospheric chemistry, ozone holes, then into astrochemistry, and then from astrochemistry into astrobiology. And if you're doing biology, then you start to think about, oh, maybe nanoparticles and things for radiation therapy. And how do you model radiation therapy? Well, it's the same thing. It's radiation interactions. It's a transdisciplinary research. And I think that's the great thing. You can do a degree in physics or in chemistry and everything else. But the real interesting things is to use your knowledge in the area that you get to work with people in another area. When the two of you get together and you build the collaborations, you can do really quite fascinating things. But most of all, why do science? Why do this? Well, because it's actually fun. And the greatest, you know, there are many disadvantages, and people like to moan about being an academic. But you know, my wife always says that, you know, if I won the lottery, I would gold plate my lab. And I say to her, "Don't be silly. I'd buy equipment for the lab because scientists are driven, and we enjoy doing things and playing with things." And I think we've never actually really quite stopped being able to have fun. And that is what I would do to anybody as you build your careers in the future. Is it's a fascinating world out there. There are loads of big questions still to be answered. There's lots of things and fascinating things to do. And as a scientist, you can explore that, but you can also maintain your fascination and learn new things all the time. And that's the best thing about being a scientist, and certainly being an academic scientist, is I learn something new and can do new things all the time. And that's not a bad career. Thank you very much.
Okay, thank you very much, Nigel. So at this segment of the talk, we're going to take some questions. I think the first hand that I saw go up, if you have a question and you want to raise your hand in the chat, please do so now, and or you can put some questions into the type chat box on the side there as well.
Yep. Any questions on anything, I will try. Lots of thank yous. Thank you.
Um,
Come on, don't be shy.
I've
Ask
got
a
a quick question, Nigel.
Yes.
So you were talking about using.
Hello.
Oh, thank you. No, please go.
Okay. Guys, I'm sorry. Is it correct that instead of like actually looking through past papers and stuff, you're playing Minecraft right now? Is it that okay, that's correct statement. Nice. Noise.
Sure. Yeah, no, carry on.
Joe.
Yeah, no problem. No, it's okay.
Don't worry, Diana.
Don't worry, no problem.
The joys of it. Don't worry. Joe, you had a question. I can't ask your past paper. I haven't seen the question. I have looked at the questions. Go on.
Sure. I was just going to quick question, Nigel. So you were talking about so combustion's a new area of research for you, and you were talking about if I'm getting this correctly, you effectively flood an area with a non-reactive compound. Is that right? So like a halide gas or something along those lines.
You need very small quantities of it. That's the point. Okay. I'm not replacing the oxygen. I'm not filling it with SF6 so you just suffocate because you've got no oxygen. You need parts per million.
So right. So it is very, very, very highly fractional.
It's so efficient. It's so efficient. It has what they call a very high cross section that you can just put it in. So it's just like an ordinary fire extinguisher, except you've just got it mixed in and you just spray it into the air, and in a dilute form, it puts the flame up. Oh. And as I say, it's because basically what it does is it takes away the electrons, and they become negative ions. They're no free flowing electrons. And this is as I say, but why that is, we don't really know. Oh. And so you might think that flames, God, people have been studying flames since Roman times. Everybody knows everything you need to know about flames. We don't. And if you are an engineer, one of your biggest problems is when you're designing power plants and everything else, and big furnaces and so on, is to try and understand how the maximum efficiency of those, and also what the pollutants are. How are the pollutants formed, and why are they formed as they are? For biomass burning and everything else. So yeah, it's interesting that you've got big textbooks. You can go, there's some in all science libraries. You can go in and find books on combustion, but actually the atomic and molecular scale of combustion, we really don't know much about it.
We had a very interesting question from, I'm terribly sorry, I can't pronounce that name. Tomas, I think that's your middle name, who was asking whether you think that there would be the applicability of this technology to larger fires potentially, rather than so obviously we're talking about fires in like a cockpit. Obviously that's in a very contained environment, relatively speaking, on a small scale. You were just mentioning that there are pollutants and other factors. How do you think this technology could work on a larger fire? Could it work on?
Yeah, that's more difficult. I mean, I think what people is probably thinking about it is, like the big forest fires and those sort of things. You would have to have a hell of a lot of material for doing that. That's why it's good for the small contained ones. The big forest fires and so on are interesting, different problems. But there was a pity. What I said, we were due to have a nice conference in November in Leipzig, but people have done some fascinating work from the Australian fires last year, and there was a lot of links to the volatile emissions given out by the plants in Australia, the eucalyptus particularly, and so on. And trying to understand why they burn so fiercely was another aspect, and it's to do with those volatiles. It's to do with the eucalyptol and so on, which even in small quantities seems to change the type of the flame, and then the transport properties of the flame. So yeah, but I think I mean what we're working on predominantly is say your household fire, your airliner fire, your transport fire, because it's a contained space. But I don't think. But people are there are some people who are trying to think about other things that they could try and put in. But I think on a forest type stuff, it's probably, well, who knows? I mean, as I say, part of the the fun of having these sort of meetings is to talk to people who are thinking about that.
We've got a question from Thomas O'Sullivan, who is asking, what do you think some of the main scientific applications would be if Perseverance finds signs of ancient life on Mars?
Well, I guess there are loads of things which would come out if we find the signs of life. The first of all is the genetics of it, the genetic code of it. Does it look like us? I mean, I don't know if you, I don't know. I grew up with Star Trek. My mother was in love with William Shatner, so I had to watch Star Trek every evening when it was on whatever night it was on, so she could get her William Shatner feeling. She couldn't watch it on her own, so I had to watch it because, you know, it was for me. But there were some good episodes on that. I don't know if anybody remembers about the silicon life, you know, that was making these balls that turned out to be eggs and so on. So does life exist in different forms is very important. I think it was interesting to hear the people talking in JPL last night, and they're on the BBC this morning. You know, they were asked the question, do you expect to find life? And the answer was, we don't find it. If we don't get evidence here, you know, it's our best place to look for it. I think if we do discover it, it is probably one of the greatest, if not the greatest landmark event in human science, human history, that we are not alone. And I think that's what drives a lot of people to do it. What are the consequences of it? Well, anything like that. I mean, we've been talking about synthetic life, trying to manipulate DNA. I didn't get a chance to talk about it, but the other thing you can do with DNA is you can use DNA as a material. You can make DNA into DNA wires, into nanowires, which are conducting by basically putting ions either into the DNA or on the surface of the DNA. And so you've all seen the sort of, you know, half human, half robot type stuff. This is not actually completely insane because you can manipulate the DNA. So I think that's one of the great things would be to see what is the life actually made up of. What we're looking for, of course, is the algae, the kind of slimy type stuff which you would find at the bottom of any pond. I mean, that's effectively what they're looking for. But nonetheless, what do those membranes look like? That's going to be the kind of key thing. Are they made of the same type of stuff as we feel that we got? Will they find something? Who knows? But if we do, and there will be a huge amount of debate about it, if we do find something that's kind of there, nobody will really say it's absolutely there until we bring it back to Earth on the Mars sample return and bring those samples back and look at them. But it would be fascinating to have some models. And our colleagues in the Europlanet project, again, some of you may have seen Caroline Smith from the Natural History Museum. She's part of the UK Space Agency today, as we just a press release saying, oh yeah, UK is involved in Perseverance, you know, because we're designing, our guys will be, Caroline and Sarah will be deciding which rocks to bring back. That's not quite true, but they'll have a pretty good say in it because they are some of the experts are looking at sort of biofossils in rocks of about the same age as they were of Mars. So that will be fascinating.
So we had a question from Pablo Sanquist. I'm not certain. Do you see computing using DNA as a possibility, i.e. using DNA as computer chips because of this viability to shape it?
It's been discussed. It's exactly been discussed. As I say, it goes back to those kind of, Arnie Schwarzenegger type movies and everything else. Yeah, I mean, people are talking about it. There is no reason why you cannot use DNA as a material. It is a material. And you can build DNA architectures, really quite sophisticated architectures of DNA can be designed and can be built. And indeed, some of my colleagues, one of my former postdocs is doing that in Germany. And they build these DNA scaffolds. In the UK, it's led by a person called Andrew Turberfield at Oxford, who are trying to build those type of structures. And they have been discussed about using them in DNA computers. We're a long, long way from it. I mean, even more further away than quantum computers are using atoms, traps, and so on. But it's been discussed. The other question just before that is how important has computer modeling been? I always talk about in astronomy we talk about three legs of a table. We have the observations, we have the laboratory experiments, and we have the models. And that's pretty much true in other things as well. In the plasma etching, you had the same. You had the engineering, you had the models, and you had the individual experiments, and they all have to work together in a kind of mutual triangle. So yeah, we do quite a lot of modeling. We've even set up some spin-out companies, which I'm involved with a couple, to commercialize those sources of what we do. The big thing now, and my other new area, if you like, maybe a bit late to the game, is machine learning and artificial intelligence. And planetary scientists have been really bad at adopting that. The astronomers are way ahead of us. But now we're getting big data sets with exoplanets. So we're having to do that. And actually, I hope I've now got my first PhD student, hopefully starting next year. We've just got a grant to do that, working with a company to try and bring over those things into the planetary science community. So modeling is absolutely vital. You can't not have it. But you do need to still, models are only good as the data you put into them. You put rubbish in, you'll get rubbish out. So you still need to understand them. They're not black boxes.
Excellent. Okay. If anybody else has any questions, feel free to put them to Professor Mason before he heads out. Otherwise, I think we can leave it there.
Yep, we're coming up to 7.
Excellent. Okay. In which case, I'll hand you back to Molly then. In which case,
right. Well, thank you, everybody. Greatly enjoy the weekend. I'm going to say it because if I don't say it, I don't know who will. I really do want us to thank all the local team, Molly, Anthony, Joe, everybody, Ali, everybody's done it. This was an enormous task, and to do it also have to do it virtually. I don't know when they actually last met as a group together, other than online. So it was a huge task, and I know they've put in an enormous amount of work, and I know that their enthusiasm for this competition is immense. And they've had some support, particularly from Sam Carr and Gunnar, and so on. But they do deserve an enormous amount of credit. And I hope during the weekend, as I say, you'll make it clear just how much you thank them for doing this, because, as I say, I've seen it, and I couldn't be more proud of you guys.
Thank you, Nigel. We really appreciate that. And thank you very much for your talk.
My pleasure. I can go back now and get dinner and then start to look at to see what the pictures coming through on the Mars are, because they should be through any moment. And please watch out for it, because there's going to be a video of the landing coming down. They've actually filmed it. It's all going to come together, and they're going to hear from the microphone what it sounds like on Mars. And you all know, being good physicists, that the sound will be different because it's a CO2 atmosphere rather than oxygen nitrogen atmosphere. So the wheels may sound different.
Very interesting. Yeah, definitely.
So it's coming soon. Great times, fascinating times. Enjoy it. Okay, guys. Good luck for the rest of the week. Good luck in your competition. And I will see you. I'll be dropping in and out, but I think I'll see you at the closing ceremony as well.
Yeah.
After Jim Al-Khalili, which will be a brilliant talk, by the way. Jim is always brilliant.
Thank you. Great. Well, I hope you all enjoyed that, everyone. We're going to have a half-an-hour break now, and then we have our pub quiz. So, Anthony, if you want to say any words about that, feel free. Everyone?
Not really. Just turn up. It's going to be on YouTube, and it will be on Zoom as well. You don't need to be participants to participate. Anyone can join in the quiz. It is a public event. I will put the Google form out in the chat. And the winning prize is £200 worth of book vouchers, which will probably buy you about one physics textbook. So, you can split it between everyone else on the team, page each or something like that.
I don't know where the IOP rep is, but I would hope that IOPP would be giving us some generous discounts on all the IOP publications.
The IOP are giving us the book voucher. That's good enough.
I'll do my best.
Okay, so if you just come back in half an hour, you can stay in the Zoom call. It'll probably be me rambling on for a bit, or just silence. Yeah. All right.
Great. Thanks, everyone. See you in half an hour, hopefully.
Okay.
Molly, would you put that form link in the chat? I can't grab it. Oh, wait, I can grab it. Don't worry. Can I? No. Yes. Oh, it's also in the Discord as well.
Okay. All right, guys. I'm gonna go and get dinner. I'll say very best of luck. I'm sure it's all going to go smoothly now. It all looks good. So we'll drop in and out during the weekend, and look forward to the talks and everything else, and hope it all goes well.
Great. Thank you. Have a nice rest of the evening. And thank you again